Hello, today we have 5 problems related to modular algebra. Greatest common divisor, lowest common divisor, modulus, stuff like that. Let's begin with the first problem. We have number a and b. We have to prove two statements. First one, if a is a multiple of t and b is a multiple of t, we have to prove that their greatest common divisor, denoted by d, is also a multiple of t. So let's begin by the fact that d can be expressed as a sum of ax plus by, where x and y is a pair of integers that we know exists. It's not arbitrary, but it does exist, so we can write out d as that. Now, t, we can pull it out of the statement, since a is a multiple of t and b is a multiple of t. We can write it down as some product like that. So essentially, this statement is a multiple of t, and since d is the exact same number, then d is also supposed to be a multiple of t. So the next one, if we have a number s that is a multiple of a and also a multiple of b, we have to prove that it's a multiple of the lowest common multiple of a and b, which is denoted by m. Okay, so let's begin by writing down as mx plus r, this nice remainder quotient form thing. Not sure how to call it properly. So x and r are integers. Now, normally we would say that r is bounded by 0 and m, where 0 is included. But in this case, we don't really care about r equals 0, because that's something we're trying to prove, and obviously there's at least one like that. You can just multiply m by whatever. But what we do need to do is prove that there is no such number that r is not equal to 0. So now what we're going to do is going to transport mx to the left-hand side. S minus mx equals r. Now the thing is, both of these things are going to be a multiple of a and a multiple of b, because m is the lowest common multiple of these things, and s is defined to be a multiple of these things. That would suggest that r is the same number is gonna be also a multiple of a and a multiple of b. Now, the lowest multiple of a and b is gonna be the LCM. In other words, r is greater than or equal to m, and we get a contradiction. So the only viable r here is r equals 0. Okay, nice. Let's continue. Let n and a be positive integers. D is the greatest common divisor. We have to show that the equation ax mod n equals 1 has a solution only if the greatest common divisor is equal to 1. Now let's rewrite the equation in a nicer form. Ax equals ny plus 1. X and y are some integers. Now let's move ny to the left-hand side. Ax minus ny equals 1. Let's say there's some number t is equal to negative y. So this can be written as ax plus nt equals 1. Now, the thing is, we know that a statement of this form with x and t arbitrary integers, every single sum like that, the lowest positive sum like that is going to be the greatest common divisor. Now, the thing is, 1 is the lowest positive number that you can pick. So there's obviously not going to be some other sum. There's going to be another positive integer that is less than 1. In other words, d is for sure equal to 1. We have proven it. Cool, let's move on. The next one. I have to show that these numbers are relatively prime for all n. Now, let's write down as the greatest common divisor in the same linear form as previously. And you can notice that a handy pick here would be to make it so n's cancel out. So let's say that a equals to 7, b equals to -5, because 7 times 5 is 35, it's the lowest common multiple of 5 and 7. But since we need to make it cancel out, we will get 35 on the left side and minus 45 on the right side. So we have a special case here. We're not going to say that it's D because we don't know if it's the lowest one just yet. 35n plus 21 minus 35n minus 20 equals 1. Now, thing is, it's just as the previous case, you can't find a lower positive integer, so D is obviously going to be 1. These numbers are co-prime. Okay, let's continue. We are given co-prime numbers m and n. We know that r is just an integer, and we have to show their integers x and y such that mx plus ny is going to be equal to r. Now, again, the greatest common divisor is going to be 1 here. It's handy to write it in the linear form. Let's not pick x because it's here. Let's pick a nicer thing. Row onto it. Let's pick p and q. Pm plus qn. Now, the thing is, we can multiply both sides by r, and the equation will still hold. Actually, let's write down that p and q are gonna be integers. Cool. So p r m plus q r n is gonna be equal to r. Now, let's define integer x as p times r, integer y as q times r. We will have xm plus yn equals r, which is exactly the statement we need to obtain. We need to prove that there's at least one pair of x and y that is going to be equal to r. So that pair is going to be p times r and q times r, where p and q are numbers that satisfy this, which we know that do exist. So we have proven it. Next one, p, q, and r are primes other than 3. We have to show that the sum of their squares is going to be divisible by 3. So obviously any of the primes, let's start with p for now, is going to be of the form 3x plus r, where r is between 0 included and 3 not included. Now, thing is, if we pick 0, this would obviously be either 3 or not a factor, a multiple of 3, which wouldn't be prime, so it doesn't match the conditions. So we can tighten up the bounds. We can say that r is either 1 or 2. Now, if we were to pick 1, notice how this is always going to be either an even number, or it can be okay, I had a brain freeze for a second, sorry. It's not always going to be an even number. It's a statement that works. Okay, then. So now let's review all of this. We have to show that p squared plus q squared plus r squared is always going to be divisible by 3. And thing is, this expression here is symmetrical, meaning that if we were to swap values of p, q, and r arbitrarily, it's still going to hold, because it doesn't matter which one of these has it. What matters is the fact that at least one of them has each of part of the 3 values. So that's cool. Now that we know that, we can actually deal with it. P, Q, and R. All of them are going to be of the form 3x plus 1 or 2, 3y plus 1 or 2, and 3z plus 1 or 2. Now, if we were to write it down in a nicer way, let's, for now, replace all of that with A, B, and C, just for now. And let's find a square of one of these things. Let's find p squared. So this is going to be 9x squared plus 6xa plus a squared. Now, the thing is, this is obviously divisible by 3, so we were to take mod 3 on both sides. P squared mod 3 is gonna be a squared mod 3. So let's review p squared. It's either gonna be for a equals 1, a squared is gonna be 1. If a equals 2, and then a squared is gonna be equal to 4, which can be written as 3 plus 1. So a squared mod 3 is always going to be 1. Now, the sum, p squared plus q squared plus r squared mod 3 is obviously going to be 1 plus 1 plus 1 mod 3, which is 0. So we have proven that it's divisible by 3. Now, I have written this statement over here only for p, but it does work for the rest by analogy. So that is for today. Bye, yeah?